Well, complex integration and all the properties of complex numbers and functions in the complex plane that we've been discussing might seem very abstract and quite far removed from the analytic combinatorics. That is our goal, and in this section we're going to see how to apply those abstractions to get us down to specific methods of getting accurate estimates, asymptotic estimates of coefficients. And it's based on a much more general class of functions than the rational functions, which are ratios of two polynomials that we have already considered. It's a complex functions that are the ratio of two analytic functions. Well, rational functions, which are polynomials, are also meromorphic, but now we're allowing functions like e to the minus z over 1 minus z, or 1 over 2 minus e to the z. And so ratio of two analytic functions of any description, a much broader class of functions. Now our approach is going to be to make use of contour integration to expand the function into terms where we can get the coefficients and then focus on the largest term to approximate. This is the same approach as we use for rationals, but we're going to have a much more general transfer theorem. So first the definition. So a function is meromorphic if it can be represented as the ratio of two analytic functions at a point in a neighborhood. Now, there's a lot of useful facts about meromorphic functions, and again, sometimes the definition is in terms of these facts, and these things are all related in complex analysis. But let's call them facts. That if you have a function that's meromorphic, then you can expand it in terms of, it's just like the analytic expansion, except we can expand it in the negative direction in terms of negative powers of z minus z0, all the way out to some finite level. And then the smallest term used in the expansion, or the biggest exponent of 1 over z minus z0, that's said to be the order of the pole. So the singularities are the places where the denominator is 0, or the poles, and where those things happen allow us to do an expansion of this sort, depending on the order of the pole or how big the polynomial is locally. And just to show this expansion, if you have a 0 of the denominator, then you can write g of z as z minus 0 to the m times some analytic function, and then just expand the analytic function f of z over that one at z0, and that's how you get that kind of expansion. Not difficult to see at all. Now, it turns out that the coefficient of z over 1 over z minus z0, which is h minus 1, that one turns out to be particularly important, and we'll see why in just a minute. That's called the residue of the function at the point, and we have a special notation for that, or the residue is equals z0 of h of z. So we can expand the function both ways from meromorphic, and we have the concept of a residue. So if we multiply by z minus z0 to the m, then we get something that's analytic. That's another way of just saying this here. Or another way to say it is that a function is meromorphic if it's analytic except for a set of isolated singularities, its poles. And at those places it's got expansions of this type. That's the characterization of meromorphic functions that we're going to take advantage of. And again, without going into details of complex analysis, I won't talk about formal proofs of all these types of things. But this sketch gives an understanding of the kind of functions that we're talking about. They can be expressed as the ratio of two analytic functions, and they can be expanded always in this form for each pole, near each pole. And the functions that we've seen are, it's usually quite easy to establish that they're meromorphic and where the poles are. So for example, derangements, that's meromorphic, except there's a pole where z equals 1. If you multiply it by 1 minus z, you get an analytic function. And this one, it's 1 over 1 plus z squared. It's meromorphic everywhere except at plus or minus I. Or this one this is the one for set partitions. There's a bunch of poles at 1, at 1/2, all the way up to 1 over r, and so forth. So in practice, it's fairly easy to determine that the function's meromorphic. It's a ratio of two analytic functions, and it's fairly easy to find the poles. It's the places where the denominator is 0. That's really the key concepts that we need to know. And this is what these things look like when we plot them. So for example, 1 over 1 minus z to the 5th has 5 poles. Those are called the roots of unity. And actually I'll talk some more about them later on. And these are just plots of what these other functions that arise look like. And we'll look at more implications of these later on. For example, 1 over 2 minus e to the z, that's got a pole whenever e to the z equals 2. Well, if z equals log 2, then e to z equals 2. But if you add 2 pi I, for 2k pi I for any value of k, you also get a pole. E to the log 2 plus 10 pi I is also 2, so you're going to get a pole. And in our plots, the poles turn up as black dots because they get larger and larger as you get closer to the pole. And we'll revisit these kinds of diagrams later on. Okay, so the first idea is to extend the Cauchy formula to integrate in a curve that goes around a pole. And so this is a result for a single pole. If you have a meromorphic function and you've got a closed loop within its domain, and there's a single pole inside that loop, then the integral around the loop is 2 pi I times the residue at the pole. That's the coefficient of h to the minus 1. And that's easy to prove from the things that we've seen. So, for example, if f of z is 1 over z, then that's got a pole at 0, and the residue is 1. That's the coefficient of 1 over z. And we saw that the integral of 1 over z dz is just 2 pi I, just using polar coordinates. And so that's an easy example. And let's look at a more complicated example. So what we can do is, because S is a pole, we can expand H near that pole and write it as a power series of this form, starting at z minus s to the n and going on. And that's really the essence of being meromorphic, is that you can write such an expansion near a pole. So now we can then deform our curve by the Cauchy theorem to a circle that is centered at S and has no other poles. Because there's no other poles in there. And then just integrate. So if we plug in the expansion and integrate, then what's going to happen is, and we saw when we did our integration example 5, that they're all 0 except for the one that is 1 over z minus s. That's the only one that doesn't cancel to 0. So that's what's left is, just to go back and look at that integration example, they all go to 0 except 2 pi I times the residue. So that's a single pole, gives us the residue. The value of the integral is the residue at that pole. So, and this is a really significant kind of calculation, because what it says is that the local properties of a function near the pole is connected somehow to properties of the function elsewhere. In this case, integral along a curve that might be distant. Doesn't matter what the curve is, it's only the local properties of the function near the pole that matter for a meromorphic function. So generalizing the integrator around a pole, we have what's called the residue theorem. If you have a meromorphic function and you have a closed loop where it's defined to be meromorphic, then an integral around that loop is equal to sum of the residues, 2 pi I times the sum of the residues. So you take the residue at every pole and add them all up, you get the value of the integral. Then here's just a sketch of that proof. It's actually almost all of it. What we're going to do is we're going to look at small circles centered at each pole. And what we're going to do is define a path. This is kind of an intermediate version of the path. That's the same as our original path, except it goes in and around and out again for each pole. In fact, it'll do the perfect small circle and out again. So for every pole, we'll take our original path, but for every pole, we'll go in and grab it and go out. Now, actually, in this curve, the poles are all outside the path. So the integral around the path is 0. We arranged it so they're all outside. Even when it's a circle like that, it's really outside the path. So the integral's 0. The in and out lines cancel out, one going one direction, one going the other direction. And the circles is the residues by doing one pole at a time. So that immediately gives the result that the integral around the path is equal to sum of the residues. So that's a quite general and powerful theorem, and then we're going to be able to take advantage of that to get coefficient asymptotics for meromorphic functions. In fact, the transfer theorem that gives nearly exact results for meromorphic functions is a direct application of the residue theorem. So the theorem says if you have a meromorphic function and you know the poles, then the coefficients of the function is just polynomials over each pole to the nth power, where the degree of the polynomial has to do with the order of the pole. And again, I'll just quickly sketch this proof. So now what we're going to do is take an integral around a big circle of radius r. We're going to take our function and we're going to divide by z to the n plus 1. And so by the residue theorem, the value of that integral is sum of the residues inside. And sum of the residues inside gives exactly these polynomials. And just for example, as the pole is of order 1, then the function grows like this constant over z to the minus alpha. So therefore the residue of the function over z to the n plus 1 is the same as the residue of this c over z minus alpha z to the n plus 1. And that's just as z goes to alpha, that just gives you alpha to the n plus 1. That's the coefficient of 1 over z minus alpha in there is simply c over alpha to the n minus 1, n plus 1. You do that for every pole. If it's of a higher order, then you start to get the polynomials. And I won't go through that detail because we'll see another way to do that in just a minute. So the value of that integral is these polynomials over a pole to the nth power. And then it's easy to bound that integral because the value of the function on the circle is going to be a constant that doesn't depend on n. So when n gets exponentially small in n. So that's a quick sketch of a theorem that gives us, with exponentially small error, a very accurate term, equation for the coefficients of a meromorphic generating function. Now, but this is complicated, and what we want to do is focus on the leading term in the same way as we did for polynomials. But before doing that, we have to consider a few points. So first one is, some of the roots might be complex. Is that going to give complications? And the answer is it surely is, because the leading term is going to depend on the distance for the origin of the pole. And all the poles are going to contribute to the leading term. So for example, there's the nth roots of unity. So those are just e to the 2 pi I k over n. Cosine 2 pi k over n plus I sine 2 pi k over n. If you raise any one of those complex numbers to the nth power, you get 1, and they're all distance 1 from the origin. And so I already showed 1 over 1 minus z to the 5th, or there's 1 over 1 minus z to the 25th. So you have 1 over those numbers to the nth power, all of them, and they're all the same distance from the origin. And we already saw an example of this phenomenon when we did the rational generating function for 1 over 1 plus z squared. That's roots of minus 1, so they're plus and minus I. And then we saw that these things mix up so that the coefficient of z to the n fluctuates and oscillates. So you have to consider all the poles that are the same distance from the origin. And that seems like that's going to be a problem, because this kind of situation might arrive and give us complicated expressions when we're trying to do analysis of this sort. But fortunately, for combinatorial generating functions, it's very often the case that there's one root that's closer to the origin than all the others. And not only that, there's a theorem called Prescience Theorem that says that if you've got a generating function that has non-negative coefficients, and of course the generating functions that we get for analytic combinatorics always have non-negative coefficients because we're counting things. And then if it's got radius of convergence r, then the point z equals r, that's a real number. It's the smallest positive real root. That one is a singularity of the function. So it means that for very many of the cases that we need to consider, all we need to worry about is the real number that's closest to the origin, and the asymptotic growth is that number to the nth power. So for example, this is a generating function that we get when considering strings containing no occurrence of 4 zeros in a row. It's got poles out there, but there's one that's closer to the origin, and that's going to determine the asymptotic growth. And not only that, the contribution from the other terms are exponentially smaller. They really can be safely ignored. So that's the implication. Only the smallest positive real root matters if no others have the same magnitude. Now, if you do have a bunch of roots that have the same magnitude, you can get really complicated periodicities. And you can read about that starting on page 266 in the book if you're interested. It's called the Daffodil Lemma, because the curves that we have to consider maybe look a little bit like a daffodil. It can get very complicated. But so many of the combinatorial classes that we've considered, this doesn't come up. There's a single root that's closest to the origin, and therefore it's real by Prescience theorem. So that's going to lead us to a much simpler theorem for the leading term of the asymptotics for meromorphic generating functions. So here's the theorem. It's the same statement, conditions as for the general theorem. Meromorphic in a closed disk of size r, and it's analytic at the origin and everywhere on the circle. If alpha is a unique closest pole to the origin, that means all the other poles are further, then it's real And not only that, we know the coefficient asymptotics. It's of the form a constant times beta to the n times n to the m minus 1, where m's the order of alpha. We have an explicit expression for the constant, and beta is 1 over alpha. That's a theorem, and that this is just a quick proof sketch. So near the pole, we can expand the function in this way. And again, since it's a pole of order 1, we're just going to prove it for m equals 1. We just have the one term h minus 1 over alpha minus z. So you want to calculate h minus 1. One thing you can do is take the limit as z goes to alpha of alpha minus z h of z. And then the approximation at alpha says our function is approximated by h minus 1 over alpha minus z. So then we can just go ahead and expand it. So 1 over alpha, so it's h minus 1 over 1 minus z over alpha. 1 minus z over alpha is some z to the n over alpha to the n. And that gives us the coefficients that the asymptotic growth is 1 over alpha to the n. And then the constant is, well, in this case, m equals 1. So it's minus 1 times f of alpha over well, we'll look at this proof of exactly where this constant comes from in a minute. That's all going to be done on the next slide. So just a couple of notes about this. So I'll complete this proof on the next slide. So as I mentioned, the error is exponentially small. Now, if they're close to the same distance, there might be periodicities for some problems that you might have to look at. Often the next term does involve some kinds of periodicities. Now, and the other thing to notice is if you go back and look at our transfer theorem for rational functions, it's the same. Well, and it ought to be the same because if f and g and z are polynomials, you get the same kind of result. But still, it's quite different paths to the same result. The residue calculus and Cauchy's theorem and so forth gives us the asymptotic result that we need for meromorphic functions. And again, we've been through quite a bit of complicated abstractions in this lecture, but really what you need to remember is these simple formulas. And in very many cases, as we'll see in the next lecture, it's simply a matter of plugging into these formulas to get the coefficient asymptotics. The essence of analytic combinatorics is we start with a combinatorial construction, and that gives us a generating function equation. And then an analytic transfer theorem like this takes the generating function equation and immediately gives us the coefficient asymptotics. Now, before I go on, I want to justify this constant. That's the coefficients. I mentioned before that we compute the constant if the poles of order 1 just by taking the limit of alpha minus z h of z. Well, if you take that limit, then you can use L'Hopital's rule, take the derivative of both sides, and so that's alpha minus z times the derivative of f plus f times the derivative of alpha minus z, which introduces a minus sign, and the bottom is g prime of z. If it's a pole of order 1, g prime of z is not going to be 0, so we can just plug in alpha. Kills the first term, and we get minus f of alpha over g prime of alpha. So that's an easy way to compute the coefficient. If it's of order 2, then we have to apply L'Hopital's rule twice. So we can do the expansion as before. We have 2 terms now, but we just take the leading term, and now our leading term, we're expanding 1 minus z over alpha squared, and then that, because of the squared, brings in a factor of n into the leading term simply by elementary generating function expansion. And then the rest of the calculation is using L'Hopital's rule twice. Take the first derivative, take the second derivative, and if it's of order 2, the second derivative is non-zero, and then taking z equals alpha kills all the terms except 1, and we're left with 2 f of alpha over g double prime of alpha. And then you can convince yourself from that that it's of order m, then our coefficient that we need is minus 1 to the m, f of alpha, mth derivative of g evaluated at alpha over alpha to m, that's the coefficient. And then the growth is n to the m minus 1, where m's the order of the pole, 1 over alpha to the n. So a simple formula for the coefficient in terms of the order of the pole. And again, there's a lot of calculations here, but I really think the bottom line is you can see some light at the end of the tunnel. We've done a lot of calculations, but what we have in the end is for many, many examples. Well, first of all, we have an analytic transfer to take a meromorphic generating function into its asymptotic growth formula. In most of the cases that we're going to consider, that we have considered in terms of combinatorial classes, the poles are order 1, so the growth is a constant times beta to the n, where beta is 1 over the closest root to the origin. So all we have to do is compute the dominant pole. Now that's the smallest root where the denominator is 0. Maybe we have to use a math package to do that, but many times it's simple, it's elementary, and should check that no other poles have the same magnitude. That's usually very easy. I usually just do it with a plot. And then what's the residue? From the theorem, it's just f of alpha over g prime of alpha, an easy calculation. And then the constant is just, now if you might worry about g prime being 0, well, if g prime is 0, then it's not order of 1, so you have to adjust to do the order of m case, but we have a formula for that too. Again, that doesn't come up in a great many of the combinatorial classes that we consider. So the constant then is just h minus 1 over alpha, and the exponential growth factor beta is just 1 over alpha. So that's the bottom line, is we've got a very simple method to transfer from generating a function equation into constant times exponential growth factor. So there has been no doubt a great deal of difficult and complicated mathematical material in this lecture, but really the purpose of it is to persuade you that there's rigor in our being able to do these kinds of analytic transfers. Most of the time, in applications, we can just use it without going back to the detailed and difficult theorems that we've talked about. So just to give just a couple of examples, so if our meromorphic function is rational, like z over 1 minus z squared, well, there's alpha, that's the root, so it's phi hat, which is the same as 1 over phi, so the exponential growth is going to be phi to the n. And what's the constant? It's phi hat over 1 plus 2 phi hat, which is 2 phi hat square root of 5 minus 1, so that's just square root of 5. And then to get the coefficient, we divide by phi hat, which takes that out, so that immediately gives the asymptotics for that generating function, which comes up in a couple of combinatorial classes. This is the generating function for derangements. So the pole is at 1, so f of alpha is e to the minus 1 is 1 over e. G prime of alpha is just 1, so it's just 1 over e divided by 1, 1 to the n. Coefficient of z to the n and h of z is 1 over e. Or to generalize derangements. So in that case, f of alpha again is 1, that's where the pole is, there's only one of them. Evaluate the numerator at 1, you get e to the minus h3, or 1 over e to the h3. Exponential growth is 1 to the n, which goes away, and divide by alpha is 1. So immediately we get the coefficients with a very simple calculation. So just as an example, here's what we're going to be doing for the entire next lecture is looking at how analytic combinatorics gets us from a combinatorial specification down to asymptotic results. So we talked about generalized arrangements. That's the combinatorial construction. And the symbolic method immediately gives that generating function. And now we have an analytic transfer to take us immediately from that generating function right down to the asymptotics of the coefficients. You don't need to know too much about Cauchy's theorem or residues or any of these things in order to be able to apply this analytic transfer theorem. So in the next lecture, we're going to see many, many, many more examples of this general idea that we can have an analytic transfer that works for a broad variety of generating function equations and takes us right to the coefficient asymptotics. So just in terms of the general form of the coefficients that I talked about at the beginning of this lecture, in the first principle of coefficient asymptotics is the location of the singularities tells us the exponential growth, and the second one is the nature tells us what about the sub-exponential factor. For meromorphic functions, if the smallest real root is alpha, then the exponential growth factor is 1 over alpha. It's that location of the singularity, closest singularity to the origin that gives us the exponential growth. And if it's a pole of order m, then it tells us the sub-exponential factor is a polynomial n to the m minus 1. That's a very, very general statement, and not only that, we have the specific way to compute the constants as well that immediately gets us accurate asymptotic results. And again, next lecture you'll see many, many examples of this. I just want to finish with an idea that this approach to combinatorial analysis is controversial in some circles. For example, this is a quote from Reardon's book, which is a very important and influential book in combinatorics. And what he said is that generating functions belong to algebra, not analysis. So it's all about manipulating the generating functions and then setting coefficients equal to learn things about counting combinatorial objects. And we saw some examples of that in part 1 of the course early on, for those of you that took part 1, like the Vandermonde convolution, which is a sum on convolving binomial coefficients that's easily proved via generating functions. And what Reardon said in his second book, combinatorialists use recurrences, generating functions, and such transformations as the Vandermonde convolution. Others, that means people who are not combinatorialists, and so they should be able to do what they want, but Reardon said, to my horror, they use contour integrals, differential equations, and other resources of mathematical analysis. Not sure what he means by to my horror. But I can remember reading quotes like this, and Reardon's not the only one, as a student, and being completely, really confused about what to do. Even for derangements, if you're looking for the coefficient of z to the n and e to the minus z over 1 minus z, you have to do a convolution. And you have to do some reasoning with that convolution to get to the asymptotic result, 1 over e. I can remember first learning these kinds of manipulations and being a little mystified by how really we get to 1 over e, particularly since it's such an accurate result. And that's just for derangements, which are permutations without singleton cycles. If you have a generalized derangement, like permutations without cycles of length 1, 2, or 3, then you've got a 4-way convolution. How are you going to get from this kind of formula to the asymptotic result, 1 over e to the 1 plus 1/2 plus 1/3, a very simple asymptotic result. And I still to this day don't understand what Reardon's plan would be for trying to solve this problem, let alone the many, many more general problems that we're able to address by using contour integrals and other resources of mathematical analysis. That's precisely what we're doing in order to get simple ways to derive asymptotic estimates for enumerating and studying properties of a very broad variety of combinatorial classes. And next time, I'll certainly convince you of that.